Hi, and welcome to 6.1 Universal Gravitation Calculations. In this lesson, students will be able to use Newton's law of universal gravitation to calculate the force of gravity between two objects. So before we talk about Newton's law of gravitation, let's talk quickly about how gravity is a non-contact or field force. And the definition of a force field is a vector field that describes a non-contact force, in this case gravity, acting on a particle at various positions in a three-dimensional space. This is a classic demonstration. This blue sheet is basically a stretchy piece of spandex, and you place a mass right in the middle of the spandex, and it warps it down. So this is used to show how space-time is warped by anything that has a mass. So if you have mass, you're actually warping space-time, and you are pulling other things with mass towards you. And those little things with mass also warp space-time, and they exert a force as well. Now, when we're talking about space-time, what we're really talking about is Einstein's theory of general relativity. But let's not get there yet. So basically, a force field, you could see in this diagram, is just describing how at any point in a region of space, you will feel a force. All right, so in this case, we're talking about gravity, and gravity acts in three dimensions. So you could pick any point in space, and you could calculate how much force is being felt by a particular object. Okay. Now, there is a really cool video. I'll post that video with the blue spandex, but this one is also showing Einstein's theory of relativity and how it relates to gravity waves. So yeah, that's pretty cool. And this is used to represent like two black holes that are orbiting each other very fast, and how that actually creates gravity waves. So if you've ever been curious about that, this is a pretty good model that shows this. Now, it is important to note that this is just a model, right? So you could see that this is pretty much two-dimensional, right? It's flat, but when you're thinking about gravity, it's in three dimensions, which is kind of hard to visualize, but this is what we use as a model to help us think about it, but it's not perfect. It's not a perfect model. So we're not going to get into Einstein's theory of relativity, but we will talk about Newton's law of gravitation. Now, there were some people that came before Newton that helped him formulate his formula. So Tycho Brahe, he built the finest observatory the world has ever seen. Look at that thing; it's beautiful. All right, so up until that point, this is the best observatory humans have ever encountered. And he studied the stars and planets' positions. He would sit under this rotunda and he would look at the stars and plot them every night. That's what he would do. He was a really cool guy. He did that every single night. And then this guy comes along, Johannes Kepler, and he was one of Brahe's assistants and mathematicians. And he comes along, and basically everybody remembers him more than Brahe. Like, I don't even know if I'm pronouncing his last name correctly. Kepler came up with the three laws of planetary motion, which you might have heard of before. So he was studying the stars and planets just like Brahe was. And the first law he came up with was that the planets orbit the sun in an elliptical shape. They were not circular, and he was able to prove that they were ellipses. Secondly, planets move faster when they get closer to the sun, as you can see in the animated GIF there. So when they're far away, the planets are moving slower, but they kind of start racing towards the sun as they get closer. And he came up with his third law, which is K is equal to R cubed over T squared. K is a constant for all planets, so that's pretty cool. He saw that there was something that was the same for everything. When you take the radius of their orbit, you cube that, and then you divide it by the square of the time it takes for one orbit, or 1 year. And when you do that math, it gets the same number for every orbit. So that was a pretty cool thing that he found. Now, Isaac Newton comes along, and he related the force that pulls an apple to the ground to the force that keeps the planets in orbit. And they say he got hit in the head with an apple, and then he just came up with this equation, but that's not really what happened. He stated that all matter actually exerts a gravitational force. So he saw that the apple was pulled to the ground, all right? Apples have matter, and he saw that the moon orbited the earth, and the moon and the earth have matter. So he was like, oh, it's the same gravitational force that causes the orbits. So he combined these three formulas and he derived an equation. So we know this one, V is equal to d over t. This was the one that Kepler came up with, and we're going to actually learn this in the next unit. It's the centripetal force formula, and it's just basically still F is equal to m, here's the m, a, so this v squared over r, that's the centripetal acceleration. All right, so when we're talking about things in orbit, we're talking about like circular motion, and he was able to use that circular motion formula to calculate this one. So this is the law of universal gravitation. The weight, well, we'll talk about it in the next slide. What do all these numbers mean, right? It looks kind of complicated. So Fg, we know it's the gravitational force. G is the universal gravitational constant. It's just a number. It's the same number every single time. The thing that changes are the masses of the objects. So you need to know the mass of both of them. And you need to know how far apart they are, specifically how far apart their centers are. It doesn't matter what this radius is. They're going to try to trick you and tell you the radius of the planet. We really are looking for the distance between the centers of the objects. All right, so that could get a little tricky. This relationship comes up again and again in physics because, again, this is describing the force of gravity, and gravity is a non-contact field force. You could also think of, if you've ever played with magnets before, all right, magnets are a non-contact field force. There's a magnetic field there, and you could use a very similar relationship. All you need to know is the distance between the magnets and how strong each magnet is, and then you'll know what the force of gravity is. So it comes up again and again because this is actually the formula for any field force. It's just that this changes, and so does this. So where the heck did G come from? There's another scientist involved. See how we all have to work together over centuries to come up with these things, and we're still learning. He found the value of G when trying to find the mass and density of Earth by using what they call, this is a torsion balance. All right, so there's just two masses suspended from a string, pretty much, and it's in an enclosed area, so there's no effect on like wind pushing it, and you could actually measure how much the wire twists, and that'll help you find G. So this is the number. Look at that. And the good thing you don't have to memorize that because that's a pretty weird looking number. So the universal gravitation constant, now we know what that is. It's going to be the same thing every single time. Now let's talk about these units real quick because that looks really intimidating. It's a Newton meter squared per kilogram squared. Why the heck would we want it to look like that? Well, if you take the kilogram times a kilogram, that's a kilogram squared, and that's on opposite sides of the fraction there, so those will cancel out. And then when you do a meter squared, this, remember, is the distance between the objects, so that's measured in meters, and then you square that, the meter squared cancels with the meter squared, and what are you left with? Newtons, and that's what we're looking for, is the force of gravity in newtons. So do you need to memorize that? No. Take out your reference table, see if you could figure out where the big G is, and then also where the formula is. Big G is the very first thing on the reference table, all right? And this dot just means times. So a Newton times a meter squared divided by a kilogram squared. You have to write the units like that in order to get credit on the New York State Physics Regents. All right, and then the gravitation formula is right here, okay? Don't get it confused with this one that's right below it. Sometimes you'll have to use one, sometimes you'll use the other. Remember, this is showing you the gravitational field strength, and this is showing you the force due to gravity between two objects, if you know what their masses are and the distance between them. So there's a couple things I like to talk about before we do the actual calculations. The first of which is how Newton's third law still applies. Gravity is just a force. So it says every action has an equal and opposite reaction. So the Earth is pulling on the moon with a force of Fg, and that's actually providing the centripetal force needed for moon to orbit Earth. But it's important to note that the moon pulls on the Earth with the same exact force. So the moon has mass, and therefore it is warping space-time, as Einstein would say, and it's pulling the Earth towards it as well with the same amount of force. And Earth actually wobbles. You know how like the moon orbits Earth? All right, it's not like Earth is stationary, and not only just because it's orbiting the sun, but there is the center of mass between these two objects is not exactly in the center of the Earth. It's slightly over here, very slightly, so it wobbles a little bit as well. It's being pulled towards the moon. The moon pulls on the Earth with the same force as the Earth pulls on the moon. Every action has an equal and opposite reaction. And you might say to yourself, how can that be? The Earth is so much more massive than the moon is. So doesn't that mean that the Earth is stronger and it's going to pull with more force? This will be bigger because the Earth is pulling it towards it. It has more mass. That's a common misconception. So instead, let's think about it like this. All right, really quickly, if you have 1 kilogram of mass here, all right, and then 1 kilogram mass on the moon, all right, then that's going to be pulled there, and this one gets pulled there. Now, this one is more massive, so boom, another kilogram. This kilogram pulls on the moon, and the moon pulls back on that kilogram. So you can see there's still like 2 force arrows here and 2 force arrows here, and it's going to balance out. Even if we add another kilogram, 1 kilogram here, it's that kilogram pulls on that kilogram, and this kilogram is being pulled on by the moon. So you could see the forces are all, they're going to be equal to each other, even if you just look at the mass now. So we could see that there's 3 arrows on either side, but look at the mass. All right, this one is more massive than this one is, but it's the same force. It's Newton's third law. So important facts about Newton's law of universal gravitation. Before we do a calculation, it says gravitational force is the mutual force of attraction between particles of matter. It's never going to be repulsion. When we do magnets, all right, there's going to be opposites attract like poles repel, but gravity is always the force of attraction. And the gravitational force is directly proportional to the mass. So just by looking at the formula, you could see, all right, the mass is on the same side of the numerator as the force is. So if I double the mass, the force will double, and we get a direct relationship. It's inversely proportional to the square of the distance between the two objects. All right, so it's going to look, what does that graph look like? What do you think? Looks like this, okay? Actually, so this looks like an inverse relationship. Inverse square is just slightly more exaggerated, but they're never going to make you pick out the difference if it was like a multiple choice problem. But that's the idea. The further you go, the larger the distance, the less force you feel. Doesn't that make sense? If you're farther away, you're moving further and further away from Earth, your distance is increasing, then the force that Earth exerts on you is going to be less. It's going to go down. And the more massive the object is, all right, the more force you're going to feel. And it's a direct relationship. All right, so it's important to also say that we're going to be dealing with a lot of big numbers. We're talking about the mass of planets and the distance between planets and moons and suns. So those are large numbers, and there's going to be a lot of scientific notation. So if you use the E button, which I highly recommend, and it's in different spots. Sometimes you'll have to do second E, or sometimes it has its own button, but you're looking for the one that has two capital E's next to each other. You only need to do it once, but that differentiates it from, there's like letters on some of these calculators too. So it's not this E, and it's not the lowercase e. I don't even really know where that is. I could look for it, but it's not, oh, it's not this E. That's different, okay? We're looking for this one with the two capital E's. So if you use that, it helps avoid errors in your calculator, okay? So try to use the E button. Let's say you have a number, it's 5 times 10 to the 15 kilograms, doesn't matter, times 10 to the, all right, that is just going to be E. So you write 5 times 10 to the is E, and then you just write 15. Nice and big like that. You don't use the caret button, you don't use anything else like that. So let's use this, 6.67 times 10 to the negative 11. How would you type that in your calculator? Why don't you try typing it now? Pause the video and see. All right, so you would write it like this, just like this in your calculator, 6.67 E negative 11. No caret, nothing like that, all right? And your calculator recognizes this as one number. Your calculator recognizes this as two separate numbers. So if you're dividing, which we will in our equation, there's a dividing, then your calculator is going to do this division first and then times the whole thing by this number and separate it out. But this, it recognizes as one number. So it's super important. I highly recommend it. And if you're not going to use the E button, at least put this in parentheses. You have to. So, quick example, it says, what is the force of attraction between 60 kilogram Juliet and 70 kilogram Romeo when their center of masses are 2 meters away? So we'll start by, again, writing the given information. So I called it M1 and M2, and then the distance, you might be tempted to make this the distance is 2 meters, okay? But when we're doing universal gravitation, we use R, and that's only, that looks like a V. We use an R. Why do we use an R? Because sometimes we'll be talking about planets and a moon, and what is the distance between these two things? All right, instead of writing a D, we make it an R. Why? Because these things are orbiting. So this is the radius of the orbit. The distance between the centers is the radius of the orbit, and that's why they use an R. Okay, so don't forget about that. Even if you're using two objects that are not orbiting each other, you can still use that R as the measure of the distance. Now don't forget to write the units for big G. All right, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And we're looking for Fg. So you write your equation, Fg is equal to big G, M1, M2 over R squared. Then you plug in. This is 6 point, actually I'll write it like I would in the calculator. Is that going to be confusing? 6.67 E negative 11 times 10 to the negative 11 times 60 times 70 divided by 2 squared. Just like that, okay? That's what you would plug in your calculator. I could rewrite it like normal. And I highly recommend you try typing this all in your calculator in one line instead of separately doing the numerator and then the denominator, because it'll just make your calculations easier. If you ever need to edit anything, you could go back in your calculator by pressing the up arrow. It makes it super easy. And if you want, you could be really paranoid and put parentheses around everything just to make sure it's separate. The numerator is separate from the denominator. All right, so that's super important. Try to do it in one line in your calculator. Pause the video and see what you get. You should have gotten 7.0035 times 10 to the negative 8. All right, and then what is the units for the gravitational force? It's newtons. All right, so Romeo and Juliet, you could calculate the force of attraction between the two of them. And as you can see, it's a very nice force of attraction there. All right, now let's do another classic pairing, the Earth and the Moon. What is the force of attraction between the Earth and the Moon? What's the gravity between them? These are actual images, and what you're seeing is actually the side of the moon that we don't normally see. They're taken by NASA, and it is a forced perspective. So it makes the moon look not only larger than it actually is compared to the Earth, it makes it look closer to the Earth than it actually is. But these are still cool images nonetheless, even if they might be a little deceiving. This is a more accurate representation of the Earth, the Moon, and the distance between them and the size comparison. Just so you know, it's kind of cool. And we went to the moon. Can you believe it? We went all the way over there. And we used the moon's gravitational pull to help us in that elliptical figure eight orbit. After you get to a certain point, then it's like you start falling towards the moon. And you could save yourself some money because you don't have to propel yourself exerting fuel the whole way. You just need to get to a point where the moon's gravitational pull is stronger than the Earth's, and then you could let the moon's gravity do the rest of the work for you, which is kind of cool. So let's do the calculation. All right, and it might look like I didn't really give you any numbers in the problem, and where do you think the numbers are? Right on your reference table. So see if you can pick out the mass of the Earth and the mass of the moon. All right, they're right over here. That's the Earth. This is the moon. So we could write down the masses. And what is the distance between the two? What is the radius that we're going to be looking for? Okay, see if you could pick it out. All right, did you look at this one? The mean radius of the Earth? No, the mean radius of the moon? No, those would tell us if you look at the diagram up there, that's this distance, the radius of the Earth and the tiny radius of the moon over there. We want this distance, the distance between their centers. That's R. That'll tell us how far apart they are, which will tell us how strong that gravitational force is. So we're looking for mean distance Earth to the moon. And mean just means average. But in this case, it's kind of like mean that they even say, oh, the radius is over here when we're looking for the radius. It's a common trick. Don't use these numbers, okay, for this example. You want the distance from Earth to the moon, this number here. And of course, we're going to use big G. Don't forget to write the units there, not little g. All right, big G. And remember that dot just means time. So you don't even need to write the dot if you don't want. You can just write the letters next to each other. Like this, it's a Newton meter squared per kilogram squared. I know it's a mouthful, but you could do it. Say it out loud right now. Say it with me. Ready? Newton meter squared per kilogram squared. Very good. Good job. Don't be intimidated by it, okay? Now it says, what is the force due to gravity? So they're looking for Fg. You see how helpful the guess method is to write the units in the first place? That way you don't have to worry about it in your calculation. So I don't expect you to write the units over here, but by having a good habit of writing the units on the side, you'll still get the points. All right, so Fg is equal to, you just plug in your numbers. And yes, even with this one, I'm challenging you to plug this in your calculator in just one line and see if you could get to the same answer that I'm going to get. And I know it's a lot. And if you're using parentheses, you make sure you put parentheses around every single one. All right, if you want, you could even put parentheses around the numerator. You could go crazy with the parentheses and then hit your divide sign, and then you could put parenthesis, that, and then put that. Like you could get really crazy with the parentheses just to make sure that you're going to get the right answer. Because if you miss some parentheses somewhere, then the calculator will do PEMDAS, and it's not going to do what you want it to do. All right. I'll even write it, so you could type it in this way if you want. You could pause the video and type it in this way. I'm going to rewrite it with the E, and you could also try it that way. I challenge you, try it with the E button. So you could try it out like that. Now I still put parentheses around my numerator just because I'm kind of paranoid about the parentheses. I've gotten enough problems wrong because of these crazy parentheses in my calculator that I just put them in the numerator, and I'll put them around the denominator as well to keep it separate when I divide. So that's what I would recommend. Make sure you have parentheses around your numerator and your denominator. And then I don't think you need this, but I do like to also, if I'm squaring this number down here, and don't forget to square it. It's an inverse square law, so it's important. I kind of put parentheses, even if I'm using the E button, around this number here, so that I know that that whole thing is getting squared, and I use the parentheses to do that. I know it's a lot. I'm really challenging you. Not, try with the E button in one line in your calculator, and you should get this answer. FG is equal to 1.99882. So I guess 1.99 times 10 to the 20. And then what are the units? Newtons. It's the force due to gravity. All right. So try it in one line. I'm telling you, you got to do it. Challenge yourself with the E buttons, even if you don't think you're going to use the E buttons for the rest of the unit because it's new and different. I'm challenging you. Try it just this once and see if you might like it or not. It makes things easier. Trust me. All right. So yeah, that's the answer there. And you can, if you want, we'll accept it. 1.99 E20. If it pops out a number that looks like that, I know what you mean. You mean times 10 to the 20. So if you write that as your answer with units, that is also an acceptable response. That's about it. Thanks for watching and have a great day.